So this is experimentally determining Avogadro's number, method number 2. So let's first do a refresher on what Avogadro's number exactly is. To do that, we're going to talk about some numbers that are used in the exact same way. 12 eggs, 12 cookies, 12 of anything make 1 dozen. Same thing, 2 socks, 2 mittens, 2 of anything make 1 pair. Avogadro's number works the same way. It says that 6.022 times 10 to the 23rd of anything equals 1 mole. So here, the mole parallels your dozen or pair as a unit of measurement. So clearly the mole talks about really large amounts. In theory, you could have a mole of baseballs or anything else, but given that a mole of baseballs would cover the Earth to a height of several hundred miles, the most practical use of it is when talking about really small things, like atoms and molecules. The mole serves as our link between this micro world and the macro world of grams and liters, which we can easily measure by mass or volume. This makes it super important in chemistry. Now, here's how we were able to experimentally find Avogadro's number through the electrolysis of water. So we set up a tub of salt water solution. You can see the H2O molecules floating around in there because the salt actually speeds up electrolysis. We then connected 2 graphite electrodes to a power source, thus creating a cathode and anode. So we're going to look at the equation for the cathode. This is our cathode right here. So at the cathode, electrons are added to the water molecules from the negative terminal. So we have our 4 electrons going in. This produces 2 molecules of hydrogen as well as 4 hydroxide ions. The hydrogen, you can see the bubbles, it starts to accumulate at the top of the graduated cylinder. Now at the anode, electrons are removed from the water, and this is why it is connected to our positive terminal. And they actually enter the electrode. This completes the circuit, so current can flow, what goes in must come out. 1 molecule of oxygen is produced, as well as 4 molecules of H+. Now, what's important to know here is that for every 4 moles of electrons, and we're looking at this big equation down here, that for every 4 moles of electrons, what we get out of it is 1 mole of O2 and 2 moles of hydrogen. Now you may be thinking, wait, the diagram and equations say 4 electrons. Where did you get 4 moles from? Remember that the mole represents a number. So if we multiply both sides of the equation by it, everything remains balanced. Now this is our setup. We've got the negative terminal wired to our cathode, and hydrogen is being collected up at the top of the graduated cylinder. For this, we only decided to measure hydrogen, but oxygen is still being produced at our anode right there. We've got an ammeter wired in, which will allow us to measure the current, but I will explain why later. So here you can see the hydrogen being produced, the bubbles moving upwards at the cathode. We have 2 key pieces of data, that the current has stabilized to be 36.6 milliamps, and that at 1,000 seconds, we have 3.6 milliliters of H2 accumulated. So the first question we need to answer is, how many moles of gas are there per milliliter at the pressure and temperature we are conducting this experiment? Well, we're going to use the ideal gas law to answer this, which states that pressure times volume is equal to the number of moles times R, a constant, times temperature. We're going to go ahead and plug those values in. We get 101,300 pascals times volume is equal to the number of moles times 8.314, the constant, times 293 Kelvin. Now, when I isolate V over N, volume per mole, we get 0.024 meters cubed per mole. Now, we're going to convert this to centimeters cubed because 1 centimeter cubed is a milliliter, and that's what we're measuring using the graduated cylinder. We're measuring in milliliters. So when you convert that, you get 24,000 centimeters cubed per mole. Now, remember how we wanted the moles of gas per milliliter, right? And right now we have it in milliliters per mole. So we're going to go ahead and take the inverse. And when you do that, you get 4.16 times 10 to the negative 5th moles per milliliter of gas. And now you may be thinking, all right, cool, but we want to know specifically about hydrogen gas because that's what we're measuring. Now, by Avogadro's law, which, by the way, is not related to Avogadro's number, Well, it states that equal volumes of all gases at the same temperature and pressure had the same number of molecules. So for this reason, we can use the value we just found for moles per milliliter when specifically talking about hydrogen. So the next thing we want to figure out is how many hydrogen molecules there are. However, in order to do this, we first have to figure out how many electrons are flowing at this moment. So we're going to go ahead and use the definition that says charge is equal to current times time, and we're just going to plug in what we know. So we know that our current is 36.6 milliamps, our time is 1,000 seconds, and we have to convert milliamps to amps, so we're going to go ahead and divide by 1,000, and we get 36.6 coulombs. Now, we want to figure out how many electrons there are, and luckily we know the charge of an individual electron, that is 1.6 times 10 to the negative 19th. So we're going to divide the charge we just found, 36.6, by the individual charge of an electron, 1.6 times 10 to the negative 19th, and we get 2.29 10 to the 20th electrons. Now, this will allow us to find how many hydrogen molecules there are. We're going to go ahead and set up a proportion from an equation we used earlier during the setup. So we know that for every 4 moles of electrons, we get 1 mole of O2 and 2 moles of hydrogen. However, we didn't measure oxygen, so we can just kind of ignore that. So we know that for every 4 moles of electrons, we get 2 moles of hydrogen. So that's where this bit comes from. So now it's just about setting up a proportion. So we have 2.29 times 10 to the 20th electrons over x is equal to 4 over 2. We can cancel out the moles from this, and we get 1.145 times 10 to the 20th molecules of hydrogen. Alright, we've got all the values we need, so we can finally set up the last equation. On the left side, we're going to put the number of hydrogen molecules that we just found, and that is 1.145 times 10 to the 20th. On the right side, we're going to go ahead and put in our 4.16 times 10 to the negative 5th moles per milliliter and multiply that by 3.6 milliliters. This bit right here gives us the number of moles. And if you notice, our milliliters cancel out and the units match up. We're going to go ahead and multiply that by Avogadro's number per mole. Now, this isn't doing anything, we're not adding anything that we shouldn't be adding. We're not affecting the balance of the equation anyway, because Avogadro's number per mole is 1. However, it's important to have that there because if you notice, our moles will end up canceling out, and we'll have just Avogadro's number here. And when we divide 1.145 times 10 to the 20th by 4.16 to the 10 to the negative 5th and 3.6, we're going to get a number value there, and that's exactly what we want because Avogadro's number is a number. So now that we know that the units match up the way they're supposed to, let's think about the thought process going on behind this. And to do that, we're going to go back to our egg example. So we say somebody tells you they have 5 dozen eggs. Okay, cool, 5 dozen, but you want to know how many exactly. So to do that, you multiply by the value assigned to a dozen, and that's 12. And that's exactly what we did with moles and Avogadro's number. So if we were going back to the egg example, we have 5 dozen, we multiply by 12, our dozens cancel out, and then we have 60 equals 5 times 12. Perfect, that's exactly what we wanted. And it's the same exact thing with Avogadro's number. So we have our number of H2 molecules, and that parallels our 60. It's just a number, right? And then we have our number of moles, this chunk here, and that parallels our 5 dozen, because that's a value right here assigned to us, assigned to a certain number of moles, right? And that's our 5 assigned to the dozen. And then finally, we want to cancel out this dozen, right? We just want that value, and then the conversion value, our 12, or in this case, our Avogadro's number. So this chunk here and this one, they parallel each other as well. So that's exactly what we did. We made sure our units canceled out the way they were supposed to, so that we could get our number value, 12, or Avogadro's number, the way we wanted it to. So all of this yielded a value of 7.646 times 10 to the 23rd. So we got a 27.01% error, which is actually pretty good considering a few different factors. One, I was hand timing this, so obviously there is going to be a degree of inaccuracy there. Two, a lot of the hydrogen bubbles were actually leaking out of the bottom of the graduated cylinder. And lastly, because some of them were actually sticking to the sides of the graduated cylinder itself, so obviously we weren't getting all of the hydrogen either way. So yeah, but 27%, pretty good. I'm happy with it. So yeah, that's it. Thank you for watching.